The first part of this chapter covers exponential growth and decay, which is a topic that you did study in Algebra 1. So here's a warm-up. If you look at these tables, I'm wondering which data set could be represented by an exponential function. So think about it. Pause the video at this time. Now, the first table is actually a linear function. The reason you would know that is, notice x is increasing by 5 every time, so x is increasing by a constant amount, and then y is actually increasing by a constant amount. So for every 5 units x changes, y is changing by 3. So this is a linear function. If you wanted to write the equation of this line, if you take y minus y, so for every 3 units y changes over x minus x, x changes 5 units, and then your y-intercept would be right here, across the y-axis at 0, 3. So that would be the equation for this function. It is a line, there's a constant rate of change. The data set then that would be represented by an exponential function is actually the second table. So how can I pick out that something is modeling an exponential function? Well, instead of adding or subtracting a certain amount, like occurs in the first table with the linear function, for an exponential function, you'd be looking, as x changes by the same amount, y is actually being multiplied by the same number. So in this case, how do I get from 100 to 50 or 50 to 25 or 25 to 12 and a half? Each case, I'm multiplying the y values by a half. How can you come up with that number? Well, okay, so if x is changing by 1, y is changing by, if I take a number divided by the previous number, or if I look lower in the table, any y divided by the previous should give me that ratio of 1/2. So if I wanted to create an equation for this function, somewhere that 1/2 would be present when I'm repeatedly multiplying by a half. On the next page, we'll look at the general equation for the exponential function. The last one, it's not linear. I'm not adding by a certain amount. It's not exponential. Here I'd be multiplying by 8. Here I'm not multiplying by 8. So if I take any number divided by the previous, I'm not getting out the same number. That means it's not exponential. So this actually, I don't know if you picked it out, this is a cubic function, y equals x cubed. So number 2, this is the only data set that could be represented by an exponential function. How do I know that? The y's are being multiplied or divided by the same number over and over and over. So that leads us to the general equation for the exponential function. Here it is, y equals a times b to the x power. Why is this an exponential function? Well, that's because x is in the exponent. There's also some key features we need for an exponential function. That number out front can't be 0. If a was 0, then you get something, like this, which would just be y to the 0. That would actually be a line. So one condition is that number out front can't be 0. Also, b can't be 1. If b were 1, I'd get something like this. Well, 1 to any power is just 1, so that would leave me with y equals a times 1. That would also be a line. So b, which is what we call the growth or decay factor, the number that I'm repeatedly multiplying by, can't be 1. On the previous example, this b value would have been the 1/2. That's what I'm multiplying by over and over and over again. Also, b has to be positive. This one's a little tricky. If I gave you something like this, where I was multiplying by -2 repeatedly, and I made a table, you've kind of got a problem because -2 to the first power is -2, -2 squared is 4, and then if I kept making a table, do you see how you're bouncing back between, you're getting out a negative value, then a positive, then a negative, and if you graphed this, this would be kind of jumping all over the place, and you don't get a smooth curve. So one other condition is that b value, the number I'm repeatedly multiplying by for an exponential function, should be positive. And then x, y in general is just any point that is on the function. So here's another way to look at it. Exponential growth. If the number out front is positive and b, or your growth factor, is greater than 1, you're going to get exponential growth. So for instance, if I see something like this, this means my starting value, or the initial amount, should be that number out in front, which in this case is 4. If I make a table, the starting amount, or the a value, should be the y-intercept. So if I plug in 0 for x, I'm going to get 4 times 2 to the 0 power. Well, 2 to the 0 power is just 1. So 4 times 1 is 4. That x-intercept, excuse me, that y-intercept, let's get out the highlighter here, there we go. That y-intercept should actually be the a value, the initial amount. So the starting amount is the number out in front. It's also the y-intercept. And then the b value is what you're multiplying by over and over and over again. So if I keep making a table, 4 times 2 to the first power, well, that would give me 8. 4 times 2 to the second power, well, now this is like 4 times 2 times 2, or 4 times 4, which gives me 16. 4 times 2 to the third power. 4 times 2 times 2 times 2, that would give me 4 times 8, or 32. So if you can see, that b value is what you're multiplying by over and over and over again. So if the b value is greater than 1, I'm going to get exponential growth. These numbers should get larger as long as that a value out front is positive. Exponential decay, if a is positive and b is between 0 and 1, so that was like the first page where I was multiplying by a half, then your y values would be getting smaller if you're repeatedly multiplying by half. So the b value is the growth or decay factor. If b is greater than 1, you're going to get growth. If b is between 0 and 1, you're going to get decay as long as a is positive. Now I want to point out a could be negative, but if a is negative, then that's just going to reflect the graph over the x-axis. So then that kind of, flips what we're talking about with exponential growth and decay. All right, so let's see where we're at with this idea. Do the functions represent exponential growth or decay? So why don't you pause the video at this time to determine whether these are growth or decay. Now here's kind of a look at what's happening if you make a table for these functions. So the first equation, y equals 3 times 5 to the x. This is an exponential function. Because x is in your exponent, I'm multiplying by a positive number repeatedly. So that a value is 3. You can see that if you plug in 0 for x, you get out 3 for y. That would be your y-intercept. So I'm starting at 3 if I plug in 0, and then if I just plug in numbers beyond 0, so if I plug in 1, I end up getting 15. If I plug in 2, I end up getting 75. What's happening here is I'm multiplying by that growth factor of 5 over and over and over and over again. So if I'm multiplying by 5, since 5 is greater than 1, this is actually going to be exponential growth. So do I have to really make a table? No, this is just the value that I'm looking at. If I'm multiplying by 5 over and over and over again, my y value should be getting increasingly larger as x gets larger. Let's jump down below. So if I go to, this function down here, 0.25 is actually like a fourth. And now you might notice, well, there's nothing out front, so that'd be like a 1 out front. If I plug in 0 for x, I get out 1 for y. So your a value here is actually like 1, and that is your y-intercept. And then if I keep plugging in values, a fourth to the first power would just be a fourth. If I take a fourth and square it, I get out a 16th. So here what's happening is as x is increasing, y is actually decreasing. It's being multiplied by a fourth. So since my b, or my decay factor, is in between 0 and 1, this is going to represent exponential decay. And let's look at the other two. So here, this would be like your starting value. If you plug in 0, you'd get out a half. That'd be your y-intercept. But really, all I'm looking at is, well, I'm multiplying by 7 repeatedly. So since 7 is larger than 1, this is going to give me exponential growth. If I start at a half and keep multiplying times 7, times 7, times 7, I'm going to get larger numbers. And then here I'm starting at 35, and if I multiply by 3/4, 3/4, 3/4, as x gets bigger, y is going to get smaller. So since 3/4 is less than 1 and greater than 0, this is going to be exponential decay. So the main thing I'm focusing in on here is that b value. And notice on all of these examples, the number out front is positive. So now let's actually look at graphing an exponential function. So I have y equals 6 times 3 to the x power. So that a value is like the 6 out front. The b value, or the number I'm multiplying by repeatedly, is 3. So since 3 is greater than 1, if I repeatedly multiply by 3, I'd be thinking immediately this is exponential growth. Now, just like graphing any other function, I can just start making a table. And in the homework, I ask you to graph points that are on each side of the y-axis. So if I start making a table, let's just start in the middle. How would I find the y-intercept? Well, for any function, if I want to find the y-intercept, I'd plug in 0 for x. Any point on the y-axis has an x value of 0. So then I take 6 times 3 to the 0. Well, 3 to the 0 is just 1. And I get out 6. So that should be your y-intercept. That corresponds to the a value here. If I plug in 1, 6 times 3 to the first power would give us 18. If I plug in 2, 6 times 3 to the second power, or 6 times 3 times 3 would give us 54. And make a note of what's happening here. So as x is getting larger, I'm multiplying my y values by 3 over and over and over again. So if I multiply by 3 again, well, 54 times 3 should give me out 162. If I go in the other direction, well, you might know what's happening here. If I go reverse this, I want to divide by 3. So I'd be thinking if I plug in -1 for x, I should actually get out 2, or 6 divided by 3 for y. So let's check it out. 6 times 3 to the -1 power. Well, 3 to the -1 would just be like 1 over 3. And what's 6 times a third, or 6 divided by 3? Yep, that gives me out 2. And let's plug in one other point to the left of the y-axis. So 6 times 3 to the -2 power. Well, that would be like 6 times 1 over 3 squared. 3 squared is 9. And 6 ninths is 2/3. Does the trend continue? Sure. If I take 2/3 times 3, I should get out 2. So now if we're graphing this, your y-intercept is right here, 0, 6. And then let's just plot a couple points on each side of the y-axis. So 0, 6. And I'm just going to kind of eyeball it here. With exponential growth, these numbers get huge really quickly. Now, think about this. If I take 2/3, if I keep going backwards and dividing by 3, so 2/3 divided by 3, divided by 3, divided by 3, I'm going to keep getting a smaller and smaller positive number, but I'm never really going to quite get out 0. I mean, you can check it out if I take, if I plug in, -10 for x. 6 times 3 to the negative 10th power would be 6 times 1 over 3 to the 10th. This is just going to give me out a really small positive y value, but I'm never going to quite hit 0. So what's happening here is I'm actually ending up with an asymptote. If you remember, the asymptote would be the line that the graph approaches but never quite touches. So here your asymptote is actually the x-axis. The equation of the x-axis would be y equals 0. Any point on the x-axis has a y value of 0. Now the growth or decay factor, we said this is growth, and I'm multiplying repeatedly by 3. So that's saying, as I move to the right on the graph, my y values, for every 1 unit x changes, y is actually being multiplied by 3. The initial amount should correspond to your y-intercept, and that would be 0, 6. So if I plug in 0 for x, I actually get out 6 for y. That's also the a value here. And let me just label a couple more points on the graph. So what did we have? 1, 18, 2, 54, negative 1, 2, and negative 2, 2/3. Okay, so there's a kind of 5 points on the graph. So what's my domain? What can I plug in for x? Well, if you notice, I can plug in anything for x. So if I plug in negative 2, negative 1, 0, positive numbers are okay. I could plug in fractions and get out values. So your domain, x can be anything. And you can see that on the graph. The graph continues left and right forever and ever and ever. So it'll go to the left, it'll go to the right, there's no gaps. Range, I'd be looking up and down on the graph, or what's coming out for the y values. Well, we talked about how I'm getting out positive numbers, but the lowest this graph ever dips, it's never going to quite touch the x-axis or the line y equals 0. So the range, I cannot get out 0 for y. I can only get out positive numbers for this equation, so your range would be any positive numbers, and you can see that the graph is above the x-axis everywhere. So key points here, this is the general shape you're going to get out for an exponential growth graph. Y is getting really big really fast because I'm repeatedly multiplying by 3. So repeated multiplication here, y is getting huge fast. So just one more graph for you to try on your own. Make a table of values, see what comes out. I would be thinking this should be exponential decay because that decay factor, or the b value, is 1/2. It's in between 0 and 1. So pause the video, sketch this out, and then let's compare our tables. So here's my table of values. One key starting point would be that y-intercept. If you plug in 0 for x, you should get out 20, or that a value for y. And then I picked 2 points to the left of the y-intercept, 2 points to the right. So 110 would be a point on the graph, and 2.5. And then if you plug in negative values for x to get a couple points on the left of the y-intercept, notice right here, big idea, if I'm raising anything to the negative power, flip it, and that fraction would, or that exponent would become positive. So 1/2 becomes 2 over 1, and then the exponent is positive. And same thing here, 1/2 to the negative 2, flip, make the exponent positive. So you'd actually have 20 times 4. Then how do I know my table's correct? Well, if you look, what's happening? As x increases by 1, so as x increases by 1, the y value is actually being multiplied by 1/2. So here's the exponential growth, repeated multiplication. So it's not like a linear function where I'm adding a certain amount. The exponential function, you're multiplying the y's over and over and over by a certain amount. That's kind of the big punch here. So let's compare graphs now. So here's the graph. I can plug in anything for x. The graph is continuous from the left to the right. What's going to come out? Well, if I keep dividing by 5, I'm just going to get very, very small y values. They're never going to hit 0. They're never going to be negative. So I can't quite hit 0, and I'm going to get out very small numbers, anything to infinity. You can see that on the graph. The asymptote is actually the same here as the previous problem, the x-axis, or y equals 0. So I'm going to approach a y value of 0, but never quite get there. And this is exponential decay because the b value is less than 1. So 1/2 is the number that we're repeatedly multiplying by, which is why everything's getting smaller. And the initial amount, or that y-intercept, is 0.20. So y-intercept, 0.20. All right, that's the start to chapter 7.